Let's consider this worked example. So we have this system here where we have a 4 centimeter piston which has force F1 which is acting upon it, and this, we're told in the question that this is 100 Newton force, and this is acting on some oil, and the oil also goes up this side. There's a 2 meter tube going up here, and at the top of the tube there's another piston 10 centimeters in diameter and another force acting on it, F2, but we don't know what this one is. We don't know which one this is. That's what we're trying to find out. We're trying to find out F2, and we're told to ignore the weights of the pistons. So the assumptions that we can make about this are that given that it's, again, we assume nothing's moving, the whole thing's in equilibrium. So all the forces and pressures in this system, all the pressures in this system are balanced, okay? So the pressure exerted by this force here is creating the pressure here, and we know that's balanced by the pressures on this side. So how do we go about calculating it? So if we first look at the pressure that's exerted by the 100 Newton force acting on the first piston. So pressure is equal to force over area. The force, as we say, is 100 newtons. The area is pi d squared over 4. So the diameter of this is 4 centimeters, but we convert that into meters. So that gives us a pressure here, just below the piston, of around 79,577 pascals. So that's the pressure there. Now, in our example, we can neglect this bit because we know the pressure here, and if this fluid isn't moving, the pressure will be the same here. So the pressure here is the same as the pressure here. So all this bit in between we can ignore. So we got to know what the pressure is on this side. We now want to know what the pressure is on this side. And this pressure is made up of two components. So we've got the hydrostatic pressure of this column of oil here, this 2 meter column, and the pressure caused by the force on the piston. So let's just consider this hydrostatic pressure first. So if you remember from the lecture, the pressure is equal to rho GH for hydrostatic pressure. So we've got the density of the oil, which is 850 kilograms per meter cubed. The G is obviously force due to the gravitational acceleration, times by the height, which is 2 meters. So that gives us the pressure, the hydrostatic pressure of the oil, which is 16,677 newtons per meter squared. So we know that the pressure on this side has got to balance out the pressures on this side. So P1 is equal to P2, which is the force due to this, plus the hydrostatic pressure of the oil. Now we now know what P1 and P oil are in this equation. We worked them out on the previous slide, but we don't know what the pressure is in the middle. But we do know that it's the force divided by this area. So therefore we can rearrange this equation, make F2 the subject, and we know the diameter of this piston, so we can work out the we know the diameter of this piston, so we can work out the area. And if you go through it and rearrange the equations, you work out that the force is equal to 494 newtons.